ARIMA and SARIMA for demand forecasting in supply chains. In this lesson, we explore how to use ARIMA and SARIMA models to forecast real-world retail demand. Accurate demand forecasting is crucial for inventory planning, order scheduling, and reducing supply chain waste. You will learn how to prepare time series demand data, build ARIMA-SARIMA models, and interpret their outputs for operational actions. Running the cell now. We import pandas for structured operational data handling. NumPy allows fast numeric and time series array operations. Matplotlib will help us visualize demand and forecasts. The SARIMAX module is for seasonal time series forecasting. The ARIMA module is for standard time series forecasting. The register function improves plotting compatibility with dates. We also import warnings to control unnecessary output. Here we silence non-critical warnings to focus on results. We activate date converters for cleaner plots. Running the cell now. Understanding real-world demand data in retail. Real supply chain data often includes dates, product codes, and order quantities. Data is usually transactional, not yet aggregated for time series forecasting. Beginners often forget to group over time periods or make mistakes with missing data. Clean time series input is essential for ARIMA and SARIMA to work properly. Running the cell now. We load a real retail demand dataset from UCI. This file tracks each product sale by date, store, and item. We make sure dates are in date-time format for time series grouping. Let us look at the shape of the raw transactions table. Previewing the first 3 records helps validate the data loaded correctly. Running the cell now. This output shows the raw, transactional retail data with over 500,000 rows and 8 columns, including order details like invoice date and quantity. Notice that the data is at the individual purchase level, with multiple rows per invoice and exact timestamps, highlighting why it's necessary to aggregate by time periods before time series forecasting. This initial exploration sets the stage for cleaning and transforming the data into a suitable format for ARIMA or SARIMA models. Practice: why is it important to convert date columns? We select only columns needed for demand forecasting, date, quantity, and product code. We exclude returns and refunds by keeping only positive quantities. We aggregate all items sold per day to get total daily demand. We set the index as a pandas date time for proper time series alignment. We fill in missing dates with 0 demand to create a regular daily series. Previewing the first week lets us see if the aggregation is correct. Running the cell now. This output shows daily aggregated order quantities after filtering out negative values, with a consistent date index including missing days filled with 0 demand. Notice how December 4th has 0 quantity, highlighting the importance of using .asfrec to fill gaps for a continuous time series. This clean, regular daily demand data is essential for reliable ARIMA and SARIMA modeling in forecasting. Beginner example 1, plotting and inspecting daily demand. First, always visualize your demand data to find anomalies or missing values. Outliers, unexpected zeros, or gaps can mean data entry or extraction errors. Running the cell now. We create a wide figure for easier visual inspection. Plotting the daily demand will reveal any trends or odd behavior. The title tells us this is overall demand over time. Labeling the x-axis helps track time. Labeling the y-axis shows the scale in quantity units. Displaying the figure lets us spot patterns or problems. Running the cell now. The plot shows the daily retail demand over time, allowing you to visually inspect for any anomalies like sudden drops to 0 or unusual spikes. Notice the overall trend and look out for any gaps or outliers, which could indicate data entry errors. This step is crucial before any analysis, ensuring the data's quality and reliability. Try: do you notice any repeating patterns or extreme peaks in the plot? Beginner example 2, checking for stationarity. ARIMA and SARIMA models assume stationary time series. Non-stationary demand can cause forecast errors or misleading signals. Running the cell now. We import the augmented Dickey-Fuller test for stationarity. We run the stationarity test on daily demand values. The ADF statistic reports how likely our demand is stationary. A low p-value means the series is likely stationary enough for ARIMA. Running the cell now. This output shows the result of the augmented Dickey-Fuller test, used here to check if the daily demand series is stationary. The ADF statistic is close to 0 and the high p-value, 0.7967, indicates we fail to reject the null hypothesis of non-stationarity, meaning the demand pattern likely has trends or seasonality. Identifying this helps us understand that the data needs transformation before applying ARIMA or SARIMA models, which require stationarity for accurate forecasting. Practice: what would you do if your p-value is above 0.05? Beginner example 3, differencing to make demand stationary. Differencing can help transform sales trends into stationary demand for ARIMA. Always review your difference data before fitting a model. Running the cell now. We compute the day-to-day difference in demand. Another wide plot is useful to visualize the changes more clearly. We plot the difference series to check if fluctuations are now around 0. The title tells us this plot shows demand changes. Labeling the x-axis keeps time relationship clear. Labeling the y-axis shows changes in sales. Showing the plot helps see if trends remain. Running the cell now. This plot shows the day-over-day changes in daily demand after applying differencing, which removes trends and makes the data more stationary. Notice how the series fluctuates around 0 without a clear upward or downward trend, indicating it's ready for ARIMA modeling. This visual check confirms that differencing successfully stabilized the demand. Intermediate example 1, fitting a basic ARIMA model. ARIMA, P, D, Q models are popular for forecasting demand where P equals AR lags, D equals differencing, Q equals MA lags. We start with simple parameters and adjust based on diagnostics. Running the cell now. We define an ARIMA model with 1 lag for AR, 1 difference, and 1 lag for MA. The model is fitted to our demand data. The summary gives us details about model coefficients and overall fit. Running the cell now. This output shows the summary of our ARIMA 111 model fitted to daily demand data with 374 observations and 1 order of differencing applied. Notice the AR1 coefficient is positive and significant, while the MA1 coefficient is negative and highly significant, indicating the model captures both short-term momentum and shock corrections. This summary helps us evaluate parameter significance and model fit, guiding adjustments to improve forecasting accuracy. Intermediate example 2, creating a demand forecast with ARIMA. The real value of ARIMA is to generate future forecasts for retail operations. We create a short-term demand forecast and visualize the results. Running the cell now. We ask the ARIMA model to forecast the next 30 days of demand. The predicted daily quantities are extracted from the forecast. Confidence intervals quantify the uncertainty in our predictions. We create a wide plot for forecast comparison. The actual historical demand is plotted first. The ARIMA forecast is overlaid in red. Shaded areas show the uncertain range, helping with risk assessment. A descriptive title helps understand the output. Labeling the x-axis clarifies dates. Y-axis labels show forecasted demand units. A legend distinguishes observed from forecasted values. We display the plot for immediate review. Running the cell now. This plot overlays the observed daily demand with the 30-day forecast generated by the ARIMA model, highlighting both the predicted values in red and the confidence intervals in pink. Notice how the forecast extends beyond the historical data, giving a short-term projection of future sales with uncertainty bounds. This visualization confirms the model's practical use in retail for planning inventory based on expected demand trends. YouTube, search for ARIMA supply chain tutorial for more step-by-step forecasting demos. Intermediate example 3, model diagnostics for ARIMA residuals. After fitting an ARIMA, always check if the residuals are random, white noise. Residuals should not show autocorrelation or obvious patterns over time. Running the cell now. We extract the model's residuals, which are the differences between predictions and reality. Create a plot for visual inspection of randomness. Drawing residuals over time reveals clusters or outliers. A proper ARIMA fit should result in randomness here. Labeling x-axis for time helps identify periods. Labeling y-axis for error magnitude provides context. Display the plot for immediate review. We import the autocorrelation function plot from stats models. Plotting autocorrelation of residuals helps confirm independence. The title highlights this is a diagnostic for model fit. Display to spot any significant spikes. Running the cell now. The first plot shows the ARIMA residuals over time, which should look like random noise without any obvious trends or patterns, indicating a well-fitted model. The second plot displays the autocorrelation function, ACF, of these residuals, where values near zero across lags confirm the absence of correlation. Together, these visuals verify that the residuals behave like white noise, validating the ARIMA model's fit. Advanced example 1, adding seasonality with SARIMA. Retail and supply chain demand often shows weekly or yearly seasonality. SARIMA includes explicit seasonal, P, D, Q, S, terms for better long-run forecasts. Running the cell now. We specify a SARIMA model with weekly seasonality, period 7. The model is fit using our demand time series. Printing the summary provides model parameters and fit statistics. Running the cell now. This output shows the SARIMA model fit summary, highlighting how the inclusion of seasonal terms, order sad smiley 111, seasonal underscore order sad smiley 1117, captures weekly seasonality in daily demand data. Notice the statistically significant autoregressive, RL1, and seasonal autoregressive, RS.L7, coefficients, which confirm the model is accounting for both short-term patterns and repeating weekly cycles, aligning with the lesson's goal of improving demand forecasts through seasonality. We forecast 30 days into the future using the SARIMA model. Predicted average demand values are extracted. Seasonal forecast uncertainty is provided by confidence intervals. We plot the observed data to provide historical context. Overlay the SARIMA forecast for comparison to observed. Green lines and shading distinguish this forecast from ARIMA. Confidence shading expresses forecast risk visually. A descriptive title clarifies this is a seasonal forecast. X-axis is for dates, grouping by week. Y-axis shows quantities. Legend explains each line. Final plot reveals both trend and seasonality handling. Running the cell now. This plot shows the 30-day forecast of retail demand using the SARIMA model, which incorporates weekly seasonality to improve accuracy. Notice how the forecasted values, in green, closely follow the observed demand's regular ups and downs, with the shaded area representing the confidence intervals that quantify forecast uncertainty. This illustrates how SARIMA captures recurring seasonal patterns, making it well-suited for supply chain demand prediction. Advanced example 2, fitting and forecasting demand for a single product. Often, we want to forecast demand not just for the whole store, but for a single stock code or item. This helps with SKU-level replenishment, automated ordering, and targeted promotions. Running the cell now. We select the SKU with the most records for better illustration. We filter the demand table to only this product. Aggregate daily demand for the chosen SKU. Format the daily index for proper time alignment. Fill in missing dates with zeros for time series modeling. Build a SARIMA with weekly seasonality for this SKU. Fit the model to the daily SKU demand. Forecast the next 14 days of this item's demand. Extract the point forecasts for visualization. Another wide figure for clear plotting. Plot the historical SKU daily sales. Overlay the forecasted demand in orange for clarity. A specific title states the SKU we are forecasting for. Label the time axis. Label the demand axis for SKU units. Include a legend to clarify lines. Show the plot to reveal the forecast. Running the cell now. In this plot, notice how the historical daily demand for the top-selling SKU is shown alongside a 14-day forecast, highlighting both recent trends and expected future demand. The consistent daily frequency, with zeros filled for no sales days, ensures the SARIMAX model captures seasonality and short-term patterns effectively. This output demonstrates SKU-level forecasting, which is essential for precise inventory and promotion planning in real retail operations. Choose another stock code to practice SKU-level forecasting. Error handling example 1, detecting and filling missing dates. Missing time periods can break ARIMA or SARIMA or distort supply forecasts. Fill gaps so every period is accounted for in demand modeling. Running the cell now. We create a full range of days for our demand period. Find which days are missing from the time index. Report the missing days so we can decide how to handle gaps. If there are missing days, display them for inspection. Running the cell now. This output confirms that there are no missing dates in the daily demand series, meaning the time index is continuous. This is crucial because gaps in dates could disrupt demand forecasting models like ARIMA by causing inconsistent time steps. Since no dates are missing, the data is ready for modeling without needing to fill any gaps. If we found missing days, re-index and fill them with zero demand. This ensures every day is present, with or without sales. If nothing is missing, keep the original series unchanged. Show the new fixed demand series shape to confirm adjustment. Running the cell now. The output shows that the fixed daily demand now has 374 entries, confirming that all dates in the full range are accounted for. This demonstrates that any missing days were detected and filled with zeros, ensuring the time series is continuous for accurate ARIMA modeling. Notice how the shape matches the intended full date range, preventing gaps that could distort demand forecasts. Error handling example 2, common join mistake with product demand. Merging wrong keys or forgetting to use both date and product code causes data errors. Always use both date and stock code in Group B or merge for multi-product demand forecasting. Running the cell now. This shows a frequent error where only date is used for grouping. This loses item-level granularity in demand forecasting. The correct operation is to also group by product identifier. The unstack operation pivots products into columns for each day. Notice the single index versus multi-index shapes for grouped results. Understanding shapes prevents model input errors. Running the cell now. The output shows that grouping only by date results in a one-dimensional summary with 305 rows, losing product-level detail, while grouping by both date and stock code creates a 2D table with 305 dates and 3,941 products. This highlights the key lesson: to accurately forecast demand for multiple products, always group or merge on both date and product keys to preserve the full dataset structure. Best practice: aggregating weekly demand for operational KPIs. Many supply chain KPIs are tracked weekly, not daily. Use weekly aggregation for smoother, actionable metrics. Running the cell now. We resample the time series to weekly sums for summary reporting. A slightly smaller plot is appropriate for overview trends. Weekly demand provides less noisy patterns. A concise title notes the aggregation period. X-axis label clarifies week boundaries. Y-axis is still product quantity sold. Displaying the plot supports operational review meetings. Running the cell now. This plot shows the total retail demand aggregated by week, smoothing out daily fluctuations into a clear weekly trend. Notice how the weekly summation makes the overall demand pattern easier to interpret, which aligns with the lesson's goal of tracking supply chain KPIs on a weekly basis for more actionable insights. Pattern: calculating a rolling service level. Rolling KPIs like fill rate or service level show how often stock meets demand. Use moving averages to smooth KPI charts for operations. Running the cell now. We use a rolling window to estimate the fraction of days with any positive demand. Another compact plot summarizes the short-term trend. Plot the 2-week rolling service level for tracking. Title makes the KPI and time window explicit. Label the date axis for operational periods. Keep the service level bounds between 0 and 1 for clarity. Visualize for ongoing supply reliability monitoring. Running the cell now. This chart depicts the 14-day rolling service level, showing the proportion of days with positive demand that were successfully met over time. Notice the smooth trend line that filters out daily fluctuations, helping identify periods of consistently high or low service levels. This visualization demonstrates how moving averages reveal meaningful patterns in stock availability, essential for operational decision-making. YouTube, learn more about KPI visualization with Supply Chain Dashboard tutorial. End-to-end example, from raw retail data to demand action. We will aggregate, clean, and forecast demand, producing a CSV with predicted next month demand. This output can drive reorder quantities and automated system triggers. Running the cell now. We fit a final SARIMA model to all daily demand. Train the best model possible with the prepared data. Forecast the full next calendar month of demand. Rename the forecast for output clarity. Save the predictions to a CSV for further operations integration. Confirm to the user that the file was saved. Running the cell now. This output confirms that the SARIMAX model has successfully generated and saved the next month demand forecast as a CSV file. Notice how the code transitions from time series fitting to producing a practical output file, connecting prediction with actionable inventory decisions. This step completes the pipeline by enabling automated reorder triggers based on the forecasted daily demand. Now opening the demand forecast CSV so we can verify and use the operational forecast for planning.